In this video, we're going to be talking about what happens inside a conductor. So I'm going to kind of imagine that I have a conductor in an electric field. So I'm going to want my electric field going this way. Okay? Now, what's going to happen is, since this is a conductor, the charges are free to move, so they will react to this electric field. So we're going to take step one, the charges in the conductor react to the electric field. In this case, the negatives move left because our electric field is pointing to the right. So what's going to happen is the negatives are going to end up on this side, and this side will have a net positive charge. Now, I'm doing this like it's the second step, but really this kind of all happens together. But there is an internal E field that is set up by the plus and minus charges. Don't draw that in red. My electric fields always point away from positive, so they're going to point back this way. So they're in the opposite direction of the original external magnetic field. And what happens is the fields end up canceling. So the net field inside is 0. So what basically happens is this, then I have my conductor and I have my electric field outside of it, but inside the conductor the electric field is always going to be 0. So this is an important rule. The electric fields in a conductor are always 0 no matter what. Now that's going to lead us to something else too. If I think of, you have to write this down, but I think of work is Q delta V. If there's no electric field in here, and again, don't necessarily draw this, that means there's going to be no force on an electron. So I can take an electron here and move it over here. There's no force one way or the other. If there's no force, I wouldn't be doing any work. So therefore, delta V has to be 0. So the voltages, or the electric potentials, in a conductor doesn't have to be 0 because the change has to be 0. The delta V has to be 0. Is constant. So if I know the voltage somewhere on that sphere is plus 8, that means everywhere on that sphere is going to be plus 8. So here's an example. A metal sphere with a radius of 2 meters carries a charge of plus 2 microcoulombs. So I'm going to kind of sketch this over here. I have my thing over here. The radius is 2 meters. And it has a charge of plus 2 microcoulombs. And we want to know the electric potential and electric field at the surface of the sphere. So first we'll find, say, the electric field. KQ over R squared. 9 times 10 to the 9th times 2 times 10 to the minus 6th divided by the radius of this thing is 2 squared. And that's going to give me a value of 4,500 newtons per coulomb. Since an electric field, I'll put some direction on there. It's going to be away from the sphere. Now, for the electric potential, V is KQ over R. So 9 times 10 to the 9th times 2 times 10 to the minus 6th over 2 this time instead of 2 squared. And that's going to give me 9,000 volts. I don't have to worry about direction. I do have to think about sign. Since it's a positive charge, I'm going to have a positive 9,000 volts at the surface of that sphere. Now, step 2, it wants us to sketch graphs of electric potential and electric field as a function of distance. So we're going to have E on this one and R. And then we'll also do one for voltage and R. And this axis, voltage, is going to be positive up here, this is going to be negative. For this, the axes, the y-axis is going to have to do with direction. This side down here would be towards the sphere, and this side up here would be away from the sphere. Now, I know that at 2 meters, the electric field is 4,500. That's what I just found. So I'm going to mark that on here. I'm going to label this as 4,500. I'm going to put a dot there. Now, as I get farther and farther away, it's going to get weaker and weaker. So I know it's going to drop off like this. All right? But what is going to be inside the sphere? When R is less than 2, I'm inside the sphere. And what we just learned back up here is that the electric field inside a conductor is 0. So inside, it's going to be 0. I'm going to put an open circle right there because right when I get to the edge, with a radius of 2, it's going to jump up to that value of 4,500, and I'll get weaker. Now, we'll do something similar for the voltage or electric potential. When R equals 2, I just calculated that the voltage is 9,000, so I'll mark that. Put a dot right here. And then it also is going to get weaker and weaker as you get farther and farther away. Okay, but what about the electric potential inside the sphere? So if I go back up to my rule, electric potential is constant. So if it's 9,000 at the surface of the sphere, it has to be 9,000 everywhere in the sphere. So that's going to look like this. Then, so that was 2. 3 says, what would it look like for minus 2? All that would change if it was minus 2 is, remember we said below the axis for this is toward the sphere. For a negative, it's going to be toward it, but it's going to be the same amounts. The equations are going to be the same. So I'm going to mark down here 4,500. And R is 2. And then it's going to get weaker and weaker and weaker, go to 0 at infinity, and it's going to be 0 inside the sphere. And then for the voltage, I'll mark 2 meters again. Again, all that's going to change is it's going to end up being negative, because voltage is going to be negative. If I have a negative charge, it's going to give me a negative voltage, so we'll have negative 9,000. And I know that point. Now it's going to get closer and closer to 0, farther away I get. And inside it's constant, so it's going to look like that.